Should I start with blue sheets?
Yes.
Actually, yes. Let's do that. How are we doing? Let's say. Oh, we should start now, right?
There's normally okay.
Yes.
Let me do this part. If you want to start over.
This afternoon, yes. My automatic good morning. That wasn't me. Good afternoon. I hope you are in the right place. This is going to be Crypto Forum Research Group. And we have a pretty full agenda, so let's get started. I'm Alexei, and Kenny, the other co-chair, is sitting next to me, so I hope you know us. We're going to start blue sheets shortly. We have a note taker. Thank you. Let's do this. So I hope you've seen note well. Rules about participation apply to this session. So same to IETF and IRTF. We have a Jabber, so people can relay stuff from Jabber, right? I'll quickly start with the document status. We finally have one more document in RFC editor's queue since last time. We also have actually 4 documents just about to be done. So basically, Kenny and I need to divide them and shepherd them through the rest of the process. So we have a couple of active documents. Verifiable random functions will be presented next time in Montreal. Couple of PEC documents, and we have a new document from Paul Hoffman about transition to post-quantum cryptography. So as far as this one is concerned, we agreed to work on the topic, but I think the research group will decide whether this document is going to be published and what exactly will end up being in the document. Yeah, we also have a couple of expired documents, but to be fair, we have quite a lot of documents to process anyway, so I don't think this is a big deal. So actually, I know. I should have asked about this earlier. Any agenda bashing? So this is our agenda. Any requests to move stuff around? All right, in this case, let's start with.
All right, thank you. My name is Karthikeyan Bhargavan, and I'm going to be talking about a new initiative called HACSPEC, which stands for High Assurance Cryptographic Software, High Assurance Cryptographic Specifications, for which I need your help. So I'm going to describe a little bit of this. This is an initiative that came out of a group of researchers who met at the sidelines of real-world crypto this year. And this is kind of a problem that we identified, and we have a proposed solution that we want your help with. So most of us will agree that implementing crypto software, which means implementations of crypto primitives, crypto constructions, correctly is hard. Okay, so if you go look at the last 2 or 3 years of OpenSSL CVEs, you'll see about half of them are memory safety bugs, like buffer overflows. About a quarter are side channel bugs, like branching on secrets, and about a quarter are functional correctness bugs, like carry propagation bugs. The thing about these kinds of bugs is that they are low probability, which means if you test and test and test the code, it's still unlikely that you might hit the case where this bug might be triggered. But an attacker who knows that the bug exists might be able to drive the implementation towards the bug. So testing doesn't work. What works better is formal verification, but formal verification requires a lot of effort and expertise. So the group came up with this idea that maybe we can try to make the effort required for verifying modern crypto primitives lower. The good news is that a whole bunch of research groups are right now able to use existing research tools to verify fairly sophisticated cryptographic implementations. So there are a bunch of tools that will verify C implementations of your primitives, including all the ones that you can imagine. There's also a few tools that will verify optimized assembly implementations. And these tools have now reached a level of maturity that they're being included in production software like boarding SSL, NSS, S2N, and so on, are actually using formal verification techniques. So the question is, well, what is the problem? The problem is that it takes a lot of effort. So how do you actually verify a crypto implementation? Well, the first thing you have to do is to write a specification that captures your desired goals. It could be like functional correctness, memory safety, some specific kinds of side channel resistance that you need, even your cryptographic security goals. And then you write your implementation and prove that this implementation meets the spec that you set out first. Okay, so both of these steps actually require work. If you go look at the various tools that are available right now, most of us agree on what the implementation languages should be, so usually C or assembly. But there is a wide variety of specification languages. So some people write specifications in general purpose logical languages like Coq and F***. Other people write it in domain-specific languages like EasyCrypt and Cryptol. And the reason we write it in these languages is that these languages, these specification languages, are particularly geared towards a specific verification method that these tools are using. However, what it means is that the first step any of us has to do when verifying code is to take the beautiful pseudocode or text written in your RFCs and encode it in the specific specification language that we have. This step is quite error-prone, quite painful, but actually is needed because this is what we need in order to get the verification tool to work. On the other hand, the negative is that the resulting spec actually looks quite different from the RFC, so it's difficult to understand what exactly we are proving. Right? So this is the kind of problems that came up when a whole bunch of us met with crypto developers in this series of workshops called Hacks, which is on the side of real-world crypto. And the developers essentially said, well, you guys have lots and lots of proofs, but we don't understand what you're proving. Okay, because the proofs are relying on the specification written in some obscure language that we don't understand and we don't have the time to learn. So this is where the idea for HackSpec came from, which is the idea that we need a language which has a well-understood syntax and semantics that both developers and crypto designers and people who are writing specs like the CFRG and so on can understand and read and write, as well as can be used as a basis for formal verification. So the design goals for HackSpec, which is a new high-assurance crypto specification language, are the following. You want the specs that we write to be really succinct and readable so that you can actually, the people in this room can read and write these specs, and that they can be integrated as pseudocode into RFCs. We want the specs to be executable so they can actually be treated as reference implementations and they will pass test vectors and so on. And we actually want them to have a clean syntax and compact formal semantics so we all can understand them and they can be used as a basis for formal verification by a variety of tools. Okay, so that's the goal that you're going for. So we have a first design. It's a very preliminary design. I'm looking for feedback. We're all looking for feedback on this. And we went around and looked at various RFCs that have been standardized recently, and we found that most symmetric crypto RFCs seem to be using pseudocode plus C reference implementations, but anything that uses field arithmetic seems to be using Python reference implementations. So we said, okay, maybe Python is the language to start with. It seems to be used by quite a few developers and designers as for prototyping and testing. So we picked a subset of Python 3.6, extended with type annotations. What is a subset? Well, it's a really, really minimal subset. We have like machine integers, we have big nums, and we have arrays, and not much else. Okay. We might add things as we need them, but we really want to keep this minimal because we want this to be a really compact and minimal domain-specific language. The types are useful in two ways. They allow us to catch very simple and silly errors, like writing into an array out of bounds, or forgetting to add one, or subtract one, and so on. But they also help us to do very precise translations into various other formal languages, which are usually typed. So in particular, we have compilers right now to F* that are already working, to EasyCrypt that is on the way, and other compilers that we're developing for languages like Cryptol and Coq. So if you write one spec in HackSpec, which looks like Python, with a few more type annotations, you will be able to get for free formal specifications in all of these different languages. We also have building a library of common constructions and specifications. We have written quite a few examples, but we need help to write more, because we want to basically exercise this language quite a bit more. What does it look like? Well, here's an example. This is the field arithmetic of poly 1305. It's a very small sort of fragment of the spec. As you can expect, it's Python. There's nothing special happening here. There's a prime, there's addition and subtraction and multiplication on this field, which is modulo the prime. But the interesting thing there is we're defining a type called FLM, which is a refinement type. It says this is a type of elements that are between 0 and prime minus 1. This means that everywhere in the spec where we use the type FLM, we will be implicitly asking the verification tool to prove that at this point, the value that we are dealing with is in the field, is between 0 and p minus 1. We can put many other such constraints. Here's a fragment of the Cha-Cha-20 spec that we wrote. Again, looks just like Python. It's nothing very surprising, except it has a few more type annotations. In particular, we are asking that all the array indexes that you use are between 0 and 15, which means that you will never accidentally access the state array outside these bounds. So again, this is just a sanity check, but it's useful to kind of put this in, and we need them for our formal models later on anyway. So once you write specs in this language, what you get is for free, you will get a compilation into models like this, which is a model in F* of Cha-Cha-20. And then you'll be able to prove that C code that looks like this implements the spec that you started off with. So you just write the spec, and then there'll be various tools that will be able to prove that assembly and C and Java and LLVM or whatever meets this high-level spec. And yes, we can verify code that uses highly optimized instructions, including vectorization and so on. There are tools that will do that for you. So coming to the end of my talk, what we need here, why I'm here is that we need some help. We want your help in promoting high assurance implementations for the standards that are coming out of this body. In particular, if any of you is writing a new crypto primitive or has just recently standardized something, maybe you want to write your pseudocode in HackSpec. Maybe in addition to your pseudocode, you want to write a reference implementation in HackSpec. So come look at our specs, read them, comment on them, add more specs if you can. Give us feedback on the language. What are the kinds of features that you might need to write specs for your new crypto primitives in this language? We are happy to kind of evolve our design depending on what people say. And help us kind of test out our various compilers to various languages and our various specs. So the code is down there. There's a mailing list which is very light right now, and you can initiate and participate in discussions there on what this language should look like. And that's all I have to say. Thank you.
Thank you. Hello, I'm Daniel Kahn-Gilmore. Hi.
Hey.
Thank you for this. This is really great, and I'm pleased to see it. One of the things that maybe you don't have an example of in your slides is how to express the formal cryptographic properties that you want from the code, right? So the examples that you showed made it pretty clear how to express numeric constraints and things like that. Can you just explain a little bit about how you use HackSpec to express those things?
Right. So right now, the way we write crypto security guarantees in these various tools, different tools have different ways of doing so. And we haven't really resolved how we would do that in a language like HackSpec, but you want to. A classic way to do that is to define two specs, one which represents the ideal functionality and one which represents the concrete functionality, and kind of show that that is the ideal functionality we want this to achieve. And the ideal functionality would not be actually executable. You can't test it, but the concrete one will be testable. And we have to show that the two of them actually achieve the same thing. And that is the goal of the crypto proof. Bit wishy-washy, we'd love some help to kind of make that more formalized.
Scott Fleur, Cisco Systems. Two questions. First one is about side channels. You mentioned that as somewhat important. Is there a way to specify that this code doesn't have any secret dependent branches or secret dependent accesses.
Yes. So for example, for our Cha-Cha 20 spec and for any symmetric spec like that, what we do is we restrict, because you have a type system, we can restrict the uses of all the integers, machine integers in this world to be secret independent, in the sense that you cannot, for example, compare two machine integers. You can only compare array indices and so on, but you cannot compare the data, which is represented by U/8. You cannot compare it, you cannot branch on it, you cannot use it as an index to an array. You can write these kinds of things, but that'll make things like AES with SBOX impossible to write in the language. So you have to relax it at some places. So you might say, okay, for the SBOX, I'll relax it. For the big num arithmetic, because you're using big nums, there is no side channel guarantee there. But once you exit that world and you come down into the world where you actually have concrete bytes and concrete integers, yes, we can express this requirement that you have to have this constant time coding discipline, which you call secret independence.
Okay. Another probably rather stupid question. I look at your GitHub and there I couldn't see any formal description of the language. Did I miss something?
Well, there's a markdown file which is extremely low content right now called language.md. It's trying to describe the language, but we are still looking for feedback, and we will formalize it all, but we first want to kind of settle on what features we actually need.
Thank you.
Phil Humbaker. Yeah, I like this a lot because we've used Python in a couple of specs.
Yeah, I've seen that.
And I've spent a lot of time trying to convert them into C# or C, because it'd be nice if you had compilers to executable languages. And if you can get C and C# and maybe Java, that basically covers all the things you need to cover, because everything else can hook into those.
That's a good point. Thanks.
Okay, any more questions, comments? Okay, from the chair's perspective, we'd like to thank you for bringing this to CFRG so early and giving us a chance to see it and get some exposure to the ideas. Yeah, please keep telling us about it as it develops. Thank you very much.
Thanks.
You can have it here. You can use it.
Yeah, I have to find the file.
Yeah, sorry.
There we go. I don't know why it does that. Oops, it's the wrong one. Beg your pardon.
Because the order doesn't matter that much.
Come on. There we go.
Okay. All right. Hello, everyone. My name is Chris Wood from Apple. Here today to talk about some work we're doing with Cass Kramers, Luke Garrett, Stanislav, not going to try to pronounce your last name because I'll butcher it, I apologize, and Nick from Cloudflare. This is something we talked about at Sec Dispatch at the last IETF, and we were encouraged to come over here to present it to you. So without further ado, the motivation for this work is that while pseudo-random number generation is fairly easy in principle and in theory and should be in practice, there are cases where they can break, and or I guess worse, they can contain more systemic design flaws. Point to just two what we consider relevant examples. First one being the Debian bug, where some developer tried to silence some warnings that were brought up by Valgrind and mistakenly removed some critical seeding processes from the or in some critical seeding step in the random number generation step, which basically hosed everyone and made the output be sort of predictable, which is not so great. And then there's the dual C bug, or design flaw, whatever you want to call it, which could have been actively exploited by TLS server implementations that happen to implement this particular spec. And that is not so great. So we're trying to bake in sort of an insurance policy or some kind of defense mechanism such that if we don't ultimately trust our pseudo-random number generator, we can still, get some guarantees about the indistinguishability of the output of the PRNG. And to do so, we build on what we call the Naxos trick, which is essentially every time we want to sample some raw entropy called X, you mix in a secret key or a private key that you have available to you, and then out pops the ultimate randomness that you would use. And this is sort of a defense in depth mentality, because if the random number generator is ultimately flawed, the security essentially, or the distinguishability essentially reduces to the secrecy of your secret key here, SK. Also, if you have sort of a systemic kind of implementation flaw or deployment flaw for some pseudo-random number generator, this technique ensures that the failures themselves are kind of localized to each individual secret key instance. So, for example, the randomness that you might get from one particular server would be different from the randomness that you would get from a different server that happened to be running the exact same RNG or PRNG with the same state. So not everyone is hosed, just a small fraction. However, in today's deployments, private keys are not readily accessible. If you're a server, you typically store them in some HSM for good reason. And if you're a client, you might keep them in an enclave. And depending on what APIs you're using to actually interface with the private keys, they might not be readily available to you. The keys themselves might be of varying types. You could have RSA or elliptic curve or whatever, meaning that the output size or whatever's fed into this mixing step is not always the same. So analyzing the randomness that comes out might not be that easy. But the commonality here is that at some point during the execution of some security protocol, they are used to compute a private key operation, be it a digital signature or encrypting something or decrypting something. And we exploit that to sort of build what we call a randomness wrapper, which essentially works as follows. Assume we have some algorithm G of X that produces X random bytes of entropy. We have a simple PRF signature algorithm and a key derivation function, which simply can be defined as HKDF extract with a empty info string. And the wrapper works sort of as written. So you would sign some fixed tag 1 with your secret key, which you can call it to your HSM or to your whatever your API that happens to manage your private key access for you, hash the output, and then anytime you wanted to extract some randomness, you would actually call it to the PRNG, get the randomness, append it to this the hash of the signature, and you would extract from that a key, the KDF step, and then you expand using the PRF however much randomness you need. I guess the KDF, we use KDF and PRF notation here, but really it's just an extract and expand kind of design. You could probably swap in whatever expander you want, of course, subject to analysis and everything to make sure that's safe. So some details about the particular parameters. So tag 1 is intended to be a fixed string that's used across, a particular deployment of this technique. So a server that starts pumping out randomness would only compute one signature with its secret key over a fixed tag, and they can just cache that value or cache the hash of that value and then never do anything with it ever again except append it to whatever randomness is generated. Tag 2 is a dynamic string. It changes on every single invocation so that you don't have colliding randomness output, and that's critically important and fairly simple to implement as well. Comment that the signature absolutely must not be exposed, otherwise all bets are off, because the point here is that, or the trick, the secret behind the Naxos trick is that the secrecy of the security of the technique relies on keeping the secret key hidden, whereas the secrecy here just relies on keeping the signature computed with that secret key or that private key hidden. And we recommend that the signature scheme should be deterministic, although if you're only doing the signature once and not anything else, perhaps that's not necessary. But again, we're trying to make no assumptions about what type of operational environment you're deploying this technique in. So you could be in an extremely hostile environment where side channels are prevalent everywhere, and perhaps computing one signature is enough to leak information. So just use a deterministic one if possible. So some obvious criticism for this technique. There was a flurry of comments on Twitter. First one being, why bother with this at all? PRNGs are very easy to get right, but just point back to the previous slide. Yes, in principle, they should be easy to get right. However, things do go wrong, and this gives us an extra insurance policy to kind of protect against those particular instances. Second major one is, why would you ever use your private key for something that's not intended to be used for? Comment here is that, or my response to that is simply here, it's not an unintended use of the private key. You're still computing a signature with a signing key. It's just not used in the same way that you would use it in the protocol originally. So for example, you're not signing the key share in TLS1 or whatever. And I'm sure other people can come up with other criticisms, and I'd be very happy to hear them on here or here at the list, or however you like. So some open issues in the draft right now. With the randomness wrapper as presented, it's not an easy drop-in replacement for something like dev random, where you just expand however much randomness you want. So we're looking at various other alternatives or various extraction alternatives to make it so that it's very easy to do so. Adam Langley had a draft a while ago that has since expired, basically specifying a CMAC-based expander instead of HMAC-based expander, and you could probably do the same thing here, where you use the KDF that's derived to, seed a key stream and then just start pumping randomness from there. We have a very trivial implementation of this technique. If you're interested, go check it out. And just comment that we could probably experiment with other implementations or with this technique in popular TLS libraries like popular VerSSL and NSS, among others, that have user space PRNG implementations that you could easily amend or wrap to make this happen. So that's it. Very simple idea. I'd love to hear any comments and criticisms you have.
Thank you. Let's go to Q&A.
Hi, Yoav Nir. So I got 2 questions. Can you go back to the formula for this? So yeah. So how bad can your PRF, your random number generator be? I mean, suppose g of x returns all zeros all the time. So does this still work? And
yes.
And the second question is, well, if your random number generator is hosted, how did you ever generate a secret key?
So we're assuming that the secret key is not generated locally. That's my answer to that particular question. Like some magical oracle says,
because
here is your
best
key.
practice is always
so
to
much
generate
entropy.
it locally.
Oh, yes.
Sorry?
Best practice is usually to generate it locally. So
I'm going to defer to the server operators on this one. I'm a client, so no. Yeah. Thank you. Oh, yeah. Nick was saying that TLS keys need to be signed and distributed. So
Martin Thompson, you don't just necessarily have to distribute private keys. So a couple of comments. Why did you choose concatenation rather than pass G to the X to the salt?
I guess no particular reason other than it was the simplest. It seemed the simplest at the time. Certainly welcome to a PR that changes it. I mean.
Okay, fine. And your assertion that this is secure in light of the XKCD random number generator that always returns 4 is not true in the case where you have the same secret key on multiple machines and they can't coordinate the generation of tags.
Everything in that case would be the same across those 2 machines. Yes, of course.
So I don't know that that's properly addressed, but I think you should probably make sure
that is a very good point to make.
Very clear.
Yeah. So while we do try to spell out that tag 1 here would be different across those 2 instances, tag 1 is like specific to the deployment of this particular instance, like maybe the MAC address and the protocol in which you're using this. Something.
Yeah.
That
leads me to the conclusion that perhaps this leads to a signing oracle that I'm not sure that I'm.
So perhaps
I was thinking this would be a fixed tag based on this is I'm using this for HTTPS server authentication, so I just pick a string that is constant across all that particular application, and then I deal with the problem of making tag 2 unique across all of the uses of the same.
Yeah, that seems reasonable. At one point, I think that maybe that was discussed. So we could certainly revisit that. Yeah, for sure.
Right. And the final thing was, if you want to work with NSS, come talk to me. We happen to have a kind of crappy random number seed that we have tried our best to remove. We just use dev-urandom on most of the builds that we have. But yeah, I mean,
I will come talk to you.
We can do this.
All right.
Yeah.
Cool.
So my question is, you mentioned that it's not a drop-in replacement for dev/urandom. Do you have any results on how many random bytes you can safely use resulting from this, or some limit?
No, not yet. Not that the security analysis, like how much we can actually pump out with this particular technique. If you're interested, if you're more like talking about performance metrics for this particular technique,
Not
not so. Okay.
more security.
So yeah, that is still a pending issue that we need to address. Like there's certainly less randomness that you can pump out with this particular technique.
The short answer is as many as you like. If you have a secure PRF and you model the hash function as a random oracle, there's really no bound.
Okay.
But you don't have forward security, though. I mean, once X is compromised.
Yes, but we just haven't specified the tightness of the bound, essentially.
Okay. Thank you.
Yeah.
I have a couple of questions too, if I may.
Yes.
At the start, you used dual EC as part of your motivation for this.
Yep.
I'm not sure that motivation really works because it's known by now that a backdoored generator in that way is actually equivalent to public key encryption, which means you can spot it in source code if you have access to source code. It stands out a mile because it's basically a public key encryption scheme. On the other hand, if you don't have access to source code, you can't see it and you can't detect it.
Okay, fair point.
So that might be something you want to look at in your, section 0 of your draft or something in terms of motivation. The other question I had is if you go back to the equation just for one moment, suppose we use this process to generate randomness for a signature scheme, which is already the signature scheme that's being used to generate the randomness.
Yep.
What can you say about security in that case?
I don't have a good answer for that right now, but that is again something we just need to kind of specify. Yeah.
Hello, Stanislav Mishlev, CryptoPro. One comment for Kenny's question. Yes, this is very important question. That's why in the new version of the draft, there at least should appear about deterministic signature algorithms. And I think we should discuss that this should can be switched to must in the future. So of course, usage of non-deterministic signature algorithm can be used only once for this exact usage and not for any other means. And about the question of Martin about signing oracle, of course, we should continue improving the draft about the form of tag 1 and tag 2, about their possible forms, such that no obvious attacks with signing oracle can be possible. So these two ways must be taken into account while we improve our draft. So thank you very much for questions. We are thinking about it already, but maybe for now our steps were not too large. But we tried to start to keep it into the account.
Yeah, thank you.
Yeah, thanks.
Thank you.
One more question from the chairs, actually, from Alexei and me is what's your intention here? What are you hoping to do?
So we were originally appointed to come here from Sec Dispatch, and here we are. So I guess
that happens a lot. People get sent to CFRG. It's like a kind of punishment thing, I
guess we're glutton for punishment. Yeah. So it depends on whatever the working or the group feels is best. I think it's a useful technique. We could certainly do it without anything written down, but hey, if it can be written down, why not?
Yeah. So Martin Thompson, let's be frank. You wrote something down in an internet draft with some intent that you would have it published. Is your intent to ask these guys and this group to publish that? Or not?
Yeah, I think so. If people deem it useful and worthy.
Excellent. Thank you.
I think chairs were sort of getting to this point, but
Thank you, Martin, for accelerating the process. So maybe we can just take a hum in the room. Are people in favor of the research group adopting this as a research group draft with the intention of as a starting point? Yeah. Potentially other techniques will come forward and other people want to get involved. And that's how it always is with an internet draft in a research group.
Yep.
So we could take a hum.
Mm-hmm.
So I guess on 3, hum if you are in favor of this, of the work of the research group adopting this as a starting point for an RFC. Okay, thank you. And hum if you are against. Did I hear a hum? Was there a hum? No?
yeah, you did.
There was one or okay, but I think much lower volume than the hum in favor. Thank you very much. It's really helpful. Thank you everyone for participating.
Yeah, thanks.
Okay, good.
Just a quick point of order. The draft is on GitHub at the link at the bottom. That's just a pointer to some code that's there. But if you have comments or you want to file pull requests, please go ahead. And you can find the slides on the agenda.
Thanks, Chris.
Yep.
Great.
All right, so the next one is about hashing to elliptic curves. This is work that Nick and I did not intend to do that, put together. There has been some work, especially with relation to the VRF draft that was recently adopted to nail down exactly how you might want to hash arbitrary strings to elliptic curves. And there are a variety of different ways to go about doing this if you just look in the literature. So we wanted to write down what we thought were reasonable mechanisms for doing so, exactly how you do them, and hopefully, depending on how this hackspec stuff goes, maybe produce some, maybe use that as kind of a vehicle to drive that particular work forward as well. So Kartik, I'm kind of, we'll sync up later to talk about it. So for some background, hashing to curves is not uncommon. It's used in a wide variety of protocols. Pakes use it quite often to hash, for example, the private key or the secret password onto the curve itself. BLS signatures used it quite frequently, or used it as well. As I mentioned, the VRF draft has a placeholder for the elliptic curve variant of the VRF that uses this particular technique. And the privacy prefs work from Cloudflare and others also has this baked into it, one step of the protocol. So the common approach to going about doing this, and the one that's written down in the VRF draft, and I think the one that's maybe implemented in privacy prefs, is the try and increment approach, where you simply iterate essentially until you hash something on the curve. So you have some string, hash it with some, concatenate with some counter, and check to see if the output can be decoded to a point on the curve. And if so, return it. Otherwise, keep going indefinitely. The problem with this particular approach is that it's obviously not constant time. The number of iterations that you do depends on, or will distinctly reveal what the actual, or may reveal something about the input. So that's not always necessary, but when we can make it constant time, we might as well. So some of the requirements we kind of set out for this particular draft are, number one, we want it to be constant time. Number two, whatever else you people want in this particular work. So question mark there, we're happy to extend that. Non-requirements are that the hash function itself is not invertible. And I realize that's kind of misleading because we typically, model these as random oracles, which we consider to be one way. But certain implementations, or certain algorithms rather, are invertible. Alligator 2, for example, which I'll point to later, is invertible. And that has some useful properties. For example, if you want to do some steganography type things where you're sending random bytes, which also happen to be a point on a curve, and you want to try and get away with it, that has a potential application there. But some particular protocols, privacy pass, for example, requires that the mapping not be invertible. So we just want to call out, and it's not yet written down the draft, but we want to call out which of these algorithms are invertible and which are not. But it's not a requirement for the ones that we write down right now. So the methods that we chose, we start with 4, are the Icart, the SWU, I forget their names, the simplified SWU and Alligator 2. And each of them has this particular requirement on the curve itself. For example, Icart requires that the order of the prime subfield is congruent to 2 mod 3. SW has no requirements, so it works for any particular curve. Alligator 2 has some interesting requirement. Q is large. I forget what the actual technical definition of large here is in this case. Has a point of order 2 and J invariant not equal to 1728. So I be more interesting to just point you to the papers for the particular details of these algorithms and why the requirements are necessary than described here. So that's what I'm doing. In the draft, we focus on one particular interface for this function, simply a hash function, which I shortened to H2C here, which takes some input alpha, maps, which is at least non-zero, and maps to some point on the curve. So alpha can be arbitrary endpoint. We use Q to denote the prime order of the base field. U is a point of order 2, specifically in the case of Alligator 2, which is the only one that has this lovely little criteria. F of x is the curve equation, and then h of x, or h of alpha, is something that we use to hash a string into the prime order subgroup of the curve, not hash to the curve, which are two distinct things. So the increment method is fairly simple. You can, write some Sage code fairly quickly to compute this. And in fact, one of the appendices in the draft has this. Some modest number of exponentiations, some scalar multiplications, and some additions and subtractions. The exact cost we still need to do in the draft, which is big to do at the end, just to compare the different, the computational, arithmetic complexity of each of the algorithms. But you can, just take a glance at it and see what it's like. Alligator 2, sort of similar, but a little bit simpler. Compute this value d, and compute the Legendre symbol, and then just, depending on what the output of that is, -1 or not, choose one value or the other. So there's some constant timeness you need to worry about with implementing this particular technique, but it's not too hard to accomplish. So our current recommendations based on the widely used curves that are in use in IETF protocols are P256, stick with simplified SW, 384 use ICART, and for 2509 and 4488 use Alligator 2, simply because those were, or that particular algorithm was sort of tailored to that, Bernstein-like world. So, and it seems to work. So I say current because those are free to change depending on what the actual cost complexity turns out to be, and if there's a new algorithm that comes out. So of course, I'm happy to discuss these particular recommendations going forward. Like I said, there's a lot of open tasks to do. We just wanted to get something written down and something that people could talk about. Need to complete the cost analysis. There's a huge empty section on the SW algorithm, particularly the details of it in the implementation, which are empty. We'll get to it eventually. Simply, that draft deadline came up on us mighty quick. So next time around, we'll get to it. Sharon Goldberg, who we collaborated with on this particular document, pointed out that it would be useful if there were security reductions in this particular work where possible. So, of course, that's something that we should consider and integrate. The interface details are sort of skimmed over, in particular how you convert octet strings to integer points. So we just need to look at the VRF draft where she and her co-authors did a great job laying out the foundations there, and maybe apply that here, and also kind of work alongside with her to see if there's something like in that draft that, or if she can point her ECVRF stuff over to this particular document so we don't duplicate work. And then I was alluding to earlier, it'd be really nice if we could use this as a driver for Hackspec to produce some verifiable implementations and test out this emerging language. And the last thing is, so I want to clarify that not all mappings are reversible. And specifically, lay out and potentially in the security consideration section, what happens if you are using a hash function that is invertible. So some open issues, in particular, the language around hashing to a prime order subgroup of the curve is not, there's much to be desired there, can certainly be fleshed out. In particular, many of the techniques that we see always multiply the output by the cofactor of the curve so that you make sure that you always belong to the prime order subgroup. That's something we've not actually written down, but it seems like a reasonable technique. And there are others that I'm not overly familiar with that we could use as well. So maybe we just stick with this particular recommendation and go from there. But of course, I'm happy to hear alternatives. The other point raised by Mike Hamburg was that you don't get pure indistinguishability from a random point in the curve for each algorithm. That's not always needed for every single protocol. So we just need to spell it very clearly, with as much technical precision as possible, what the indistinguishability guarantees are, and potentially list some algorithm or some protocols in which this is not needed. So that's still sort of an open task, and I'd be interested to hear what people have to say or think about that. And so that's it. So I encourage you, if you're interested, go take a gander at the graph. It simply lists the different algorithms, has some implementations, and has some to-dos that we need to fill in. And yep, that's it.
Questions, comments, feedback? Do people think this is useful? desirable? Please come to the mic and give your reasons why. It would be really helpful. Or not.
Oh, someone's coming.
Thanks, Richard.
So I actually have a question, Richard Barnes. Question about a variant, whether this is related to a different problem that I've got in a different context. So in the MLS stuff we'll be discussing at the BOF on Thursday, we have a need to map from a random string to a curve point, but also with a known discrete log. So we want to map to an EC key pair instead of just a point. Now that draft has something in it that I just sort of made up and I think looks kind of okay, but do you think there are like learnings here that could apply to validating something, a mapping of that type as well as a mapping to points itself?
So I would need to look at it, and it sounds like, yeah, sure, maybe. That's as good as answer I can give right now.
Later.
Yeah, so we'll talk, and then we'll see if there's some way we can kind of expand the interface here to accommodate that particular use case or something. Yeah.
It could be a little bit dangerous though, because in here you're trying to kind of get some kind of random oracle functionality onto the curve, right? From strings to curve points, and you're doing something that's manifestly not a random oracle. So
that may actually be an interesting question for MLS, whether we actually need that property out of the derivation we've got.
Yeah.
And I don't think we've looked at that.
okay.
It is also interesting in the VRF draft, the interface is not exactly equivalent to this. They take in a public key and a string, and they use both in hashing to a point in the curve. So the question of what exactly is the right interface here is still, of course, up for discussion. We just chose, one input, the arbitrary input, because, as Kenny said, we kind of want that to be the thing that we hash onto the curve and nothing else. But of course, we can talk about it if we need to change it.
Okay, so here is grilling one. So I would like to know, did you have some comparison with your proposal with other existing solutions in both aspects of security and efficiency?
We don't have a proposal. This is simply a collation of all of the existing techniques and algorithms that have been already published into a single document in an attempt to kind of nail down exactly how you would do this if you were to do this in an IETF protocol. Because it's used quite often. And I just point to the VRF draft as one particular use case. So I'm sure somewhere like for example, in the Alligator paper and in the simplified SW paper where they presented that particular algorithm, they do offer comparisons between their work and all those published previously.
Yeah.
So maybe we can yank those in with proper citations and yeah.
Okay, great. Yeah, just would like to know this.
Yep.
Yeah.
Of course.
Hi, I'm Ella Berners-Lee. I was just wondering, were any of the curves that you just mentioned pairing friendly?
Not that I'm aware of, no.
Okay, because I know there is a publication out there about implementing hashing onto BN curves. So is there any interest in adding that into the draft or?
So I'm not opposed to it. Nick, my co-author, is shaking his head yes. So yes, there is interest.
Okay, great. And one more question. When you talk about not being strictly indistinguishable from random, what kind of language does that look like? Is that sort of just losing a couple of bits of security, or do we say it in a completely different way now? Or?
So to give you an example of the extreme, Alligator 2 only hashes onto half of the points on the curve, so that's slightly indistinguishable, or that's slightly distinguishable. We don't. Sorry, we're not more precise than that. We would certainly like to be, though. And if you have suggestions, we'd love to hear it. Thanks.
Dan Harkins. Yeah, I think this is a really good idea. It's very important. As you mentioned, it is used in VRF. It's used in PAICS. I got beaten up pretty severely for using a really simple and lame way of hashing to elliptic curve. And had this been around, I wouldn't have gotten beaten up so badly. So
good.
I'd probably get beaten up anyway.
Okay.
Scott Fleur, Cisco Systems. I'd like to emphasize if you have a method which misses half the points on the curve, that is very critical that you emphasize it. It will completely break most PAICS.
Yes, absolutely. And we do not go into strong language there. We simply, actually, I don't think we write down that it only, maybe we do, maybe we don't, I don't recall. But if we do not, it is certainly an omission and it should be added. Yeah.
We're on time.
We're on time.
So, don't read all the questions. Okay, my turn then. Chairs would like to ask if there are any objections to adopting this document as a research group document, with the assumptions that, more changes will be done and, more curves will be added as discussed. Yes, and stuff. Are there people who are willing to work on this document? Review document? All right, that sounds good. Thank you.
Thanks, everyone.
Hi, I'm Nick Sullivan from Cloudflare. This is sort of the Nick and Chris show right now. But right now, I'd like to introduce this draft that we wrote that introduces a new construction called Verifiable Oblivious Pseudo-Random functions. Now, it builds on the intuition from two very well-known constructions. One is VRFs, which is a public key analog to hashing. So you can compute a VRF and then someone can verify that with your public key that this was done correctly. This has several applications, including key transparency and the NSEC5 draft as well. So this is a very useful technique in a lot of different areas of cryptography. Another basic construction is that of OPRFs, which is similar to the idea of blind signatures, which was rooted in the idea from eCash schemes. Generally, how this works is someone will take a message that they want to have signed by a signer and blind it in some way, send the blind message to the signer, who then signs it, and it can be returned and then unblinded. And then any person with the public key of the signer can validate that this signature and message were signed. But this has the additional property of obliviousness, where the signer does not know at the time of signature anything about the message that was signed, just that it had signed a specific blinded object. Now, the intuition for VOPRFs is to kind of combine the best of both of these. You lose some properties, but essentially, if you go through what a VRF or what a PRF is supposed to be, is that it's a function that given x, it's infeasible to compute this function without knowing a secret key, K. And this f is also supposed to be indistinguishable from random. And this has the technique that we want to incorporate from VRFs here is that this should also be verifiable. So somebody who requests this VOPRF to be computed can verify that it was actually used, it was computed using a specific private key that's associated with a known public key. We would also like this to be oblivious in that the signer does not know if the value y that is revealed to them cannot identify which x was actually used or which computation was actually used to compute y. So yes, if x is revealed to the signer, they can't actually identify which signature or which of these computations is the one that was used to compute it. So this is very similar to the VRF and the OPRF, but what you do, these two verifiable and oblivious properties are used together, but you lose the ability to have this publicly verifiable. So if you do actually expose this as a publicly as a public value, then the signer can then recover the obliviousness. So the way that it kind of will fit into a protocol is as such, the verifier will construct a message M, will blind that message, send it to the prover, which will then compute a signature, S, a signature, which is the OPRF computation, VOPRF computation. The verifier can then take this and verify that this is associated with the prover's public key. And then they can remove the blind, and if they want to, they can confirm the output here. This signature is associated with the original message M, send that back to the prover. They can verify the same thing. And this original VOPRF computation versus the confirmation, these are unlinkable. There's no way to associate M prime with M without actually seeing the associated proof. So this can actually be instantiated with elliptic curves. This is very similar to the work in the VRF draft that was discussed in the previous presentation. So you can construct it with an elliptic curve, a one-way function that, as was described in the previous presentation, a one-way hash to curve that takes a value, a string, and puts it onto the curve. And if you also have a way to do a non-interactive zero-knowledge discrete log equality proof, so that's a very long phrase, but essentially what it means is that given two pairs of points, you know that they were both exponentiated with the same scalar. So we have a warning. Edurome authentication failed. Great. Okay, let's go forward. So this instantiation was actually came from a paper from a few years ago from Jarecki, Kiais, and Krawczyk, and this describes the algorithm which lets you compute a discrete logarithm equivalence. So if you have y modulo point g and z modulo point m, you can show that they're actually have been exponentiated with the same scalar k. And these are the details of the algorithm. And in the protocol, some intuition you can get around this is you take your string, which is your sort of secret value, you hash this into a curve, and you apply a blinding factor, which is just an exponent, which is just a multiplicative value here. So your message that you're sending to the server, or to the prover in this case, is the hash of the input x onto the curve. So you have a curve point, and you multiply it by a blinding value r. On the prover side, you take that value and you multiply it by the secret key. In the case of hash curve, this is just another secret scalar. And then you generate a discrete log equivalence proof between this multiplication of the point and a public pair that represents a base point, and the base point multiplied by, again, k, which is the secret value on the prover. You can send this back, and the verifier can verify this discrete logarithm, sort of divide out its multiplicative factor r by multiplying by the inverse, and you end up with the original point hashed to a curve multiplied by the prover's private key. Now, the second phase of this in some protocols is that you can take this pair and send it to the prover, who can then compute a hash of the value x and multiply by its private key, and that should be equal to the original value y. And if it is equal, then it knows that its private key was used in the computation of y, but it does not know exactly which value it originally computed, because it doesn't know the discrete logarithm modulo the blinding factor. So the blinding factor is what keeps this from being known to the server. So this adds the obliviousness. So if these match, then you can confirm, yes, this was actually used in a previous interaction. Alternatively, you don't have to send the value y. You can send a value that can only be computed with the knowledge of y. And the prover can compute that same y as well by multiplying that x hash to the curve by k. And then you can validate that both parties share this y over a specific, bound to a specific message. So that's generally how this construction works. And as was mentioned before, we have an application to this called Privacy Pass, which is in an upcoming PETS paper with myself and Alex Davidson and a few other folks. The way that this works, this is for reducing the amount of CAPTCHAs seen on the internet in a privacy-preserving way. So the way it would work is that you would compute a token or a set of tokens, and when solving a CAPTCHA, the CAPTCHA server will compute the VOPRF over your blinded tokens and send them back to you. And then the next time you see a CAPTCHA on a completely different site, on a completely different origin, you can submit the unblinded token. And then the server has no way to actually associate whether or not, which site was the one that actually issued these tokens. So it allows you to send data to prove that you have solved a CAPTCHA on another site without revealing which origin that site was originally presented at. So this allows a sort of bypass of the same origin policy due to the blinding ability of the VOPRF. And this is implemented in a browser extension for Chrome and Firefox, as well as on Cloudflare servers. Another potential application of this that we've looked into is privacy-preserving password leak checks. So if a service has a lot of passwords that have been leaked, what they can do is they can hash these to a curve and exponentiate by a private value. And if you want to check whether your password is part of that list, you can submit it to the server to compute a VOPRF and have it come back, and then compare it with the entire database. And what this lets you do as a server that has access to all of these, the private keys for all these passwords, is to do rate limiting. So it allows you to check to see which password you're looking for, and the server doesn't get to know which password you're actually looking for. So if you have a unique password, it can't identify you, as well as it stops people from being able to do kind of a brute force crack of all these websites, because it requires this VOPRF computation. And these are some of the foundations for this, is several different papers, and as well as this relies on the previous presentation, which is about hashing to elliptic curves. This is one of the major motivating factors for writing that document. And that's it. Questions?
Stunned silence, more like. It's the zero knowledge proofs, Nick.
Yeah, exactly.
You get people every time. Oh,
we'll see if Antoine has something
Here
to
comes
say.
Antoine. Thank you.
This is Antoine Derigna from MSR. I'm kind of struggling to understand what is the actual contents of your draft that you're proposing. I didn't read it, so I'm trying to understand, because you talked about several kind of cryptographic primitives, so many of which are kind of fancy, but from my understanding of these primitives, they have kind of different security models. So I want to understand what exactly you're trying to propose as a standard.
Right. So what this draft contains is a general definition of VOPRFs, how they work, and a specific instantiation that you can do given an elliptic curve as well as a hash to curve. So if you have a specific curve that you like and you have an algorithm to hash to it, that is one way. This tells you how to construct a protocol of this sort.
Okay, and to which extent is your draft specific to one particular construction of VOPRF?
In particular, this draft is about this elliptic curve instantiation. We don't go into opening it up to more generalized VOPRFs. It can be instantiated in different ways, but this draft is about EC VOPRF.
Okay, and nothing about other kind of VRF?
No, there's nothing about that. It's just the specific definition of this instantiation.
Okay. Thank you very much.
Okay. Do you want to ask anything about this? What are we going to do with this?
What are you going to do with this, Nick?
What do you want us
Are
to
you
do?
looking for research group adoption of this draft? Presumably, yes.
Presumably, yes. I mean, based on whether or not the hashed curve is adopted, I think this is a fine follow-on to that work and dependent on it.
Okay. Do you see them progressing in parallel or in sequence?
I think they can progress in parallel, and I also think that things like Privacy Pass as a protocol could be proposed for, say, the HTTP working group or something like this that would rely on this draft being adopted.
Okay. So are there people in the room who would, in addition to the authors of the draft, who would be interested in working on this? Maybe, go ahead.
Hi, Daniel Kahn-Gilmore, ACLU. Sorry, that was really loud. I am really grateful to see this work happening. One of the concerns is about how you ensure that the key, for Privacy Pass in particular, that the key remains constant, right? Or else the person doing the signing can keep a single key. I believe you've solved that for the Tor arrangement. Do you have suggestions for how to solve it for?
I think in general, making sure that the server does not. Yeah, so what you're mentioning is the tagging attack, where the server could potentially provide a proof to a different public key that is unique to you, which sort of defeats the privacy properties of this. And the general suggestions for this are to make sure that the server's public key or the signer's public key has some sort of public verifiability, whether it's put in some sort of consensus protocol or part of certificate transparency or some sort of transparency log. And the hope is that every signer, every verifier interacting with this system would also have access to this. But I think that's outside of the scope of this particular document.
Okay, that's what I was looking for, was whether you see that as being independent of this.
I think it's independent in the way that certificates are independent of TLS.
Okay, that's fine. I just want to make sure that if we do end up working on a document like this, there needs to be a big caveat in it that says, to use this scheme safely in public, you need something like, so that that's not.
Yeah, noted. And we should definitely add that text to the draft.
Okay. We'll take it to the mailing list, and we'll have follow-up discussions with you. So,
thank you.
So is that? Okay. So hello everyone. My name is Guilin Wang from Huawei. So my talk is about PAKE. So PAKE, password authenticated key exchange. So in the first part, I will introduce background about PAKE. Then we will introduce our proposals. Our protocols. Yeah. Then we will consider whether it's a good candidate proposal for the RFC 8125. Because it gives some requirements about the PAKE. So here is the terminology or some main concepts about the PAKE, in case you are not so familiar with this one. PAKE basically means it allows two parties to establish a secure key in the crypto sense by using a common shared secret between two parties. Because the secret is assumed as very short, so it is easy to memorize. But on the other hand, this also means it just has a low entropy. It could be very easy for attacker to guess the password. So the main thing we need to think about the security of the PEG is about the dictionary attack. Actually, two versions. One called the online dictionary attack. This can be prevented quite easily by supposing the server side can do some check. Just allow you try the password for a few times in a given period. This can be done very good in practice. So the really difficult one is about the offline dictionary attack. It means that actually an attacker can listen your messages for your protocol, for several protocol running instance. After that, they can, according to this message, and try to do offline calculation to find your password. It's a big problem. Because the password is short, and many people use the password according to some particular information, like your name or your birthday, something like this. So attacker can create a dictionary for possible password and try this one by doing offline calculations. Offline, they have computers, even super powerful computers, can do it very quickly. So this dictionary size can be very big, actually. Another security requirement is called the forward security. It is also important. Basically, it means we would like to have such a PEG protocol such that even the password is leaked sometime later. Even in this case, the purveyors share the secret key, the session key, agreed by using the password can still be secure. This is important one. One more thing is that actually original version about the PEG is that both parties just share the raw secret, the password. But in this case, especially if the server is compromised by attacker, so the server can get the password for all the users. This will be very bad. So we would like to have something else. This is called the how to prevent the server corruption or compromise. This means even if the attacker get compromise the server, they can only get some information about the password, but not the password itself. So to do this one, we have a variant of PEG called the Verifiable PEG. So we can call it the VPAKE. In this case, we can prevent the server corruption. So this is the terminology. A little complex, but if you know this quite well, it is actually quite interesting. Okay, so the main challenge for the PEG is that we would need to design PAKE secure against the offline dictionary attack. This is the challenge part. So the main limitations is that most of existing PEG solutions are two aspects. The first one is quite a number of them actually do not support forward security, but this one is actually important. And another one is that for some schemes, they have provable security, but only in the multiplicative groups of finite fields. Basically, it means it does not work for elliptic curve, not work for ECC. ECC actually important one, especially if you need to consider efficiency, because it can use the short elements and can get very tight security key. So it is more efficient for both computation and communication. So we have two protocols, PEG protocols, which meet both forward security and can work in any group, so including ECC, which means. So the paper actually published in 2000 ACM, Asia CSS, a nice conference just 1 year ago. And a public version is actually available from the Professor David Ponchiva's website from ENS. So you can get the version as well. So these two protocols, we call them TBPEKE, two bases, password exponential key exchange. So two base just a term. We use how to construct the protocol. And the verified version called the VTBPEKE. So this can be used to prevent the server corruption. Yeah, so both protocol can be proved secure under standard complexity assumption. So this means we have a cryptographic security guarantee for these protocols. And the most important one is that ECC can be used to implement the protocols. So in this case, both computation and communication can be quite efficient. Okay, so here is some very quick summary about the existing solutions. There is a lot actually. Here I just mentioned two most famous one and also quite related to our research work. The first protocol called the EKE, Encrypted Key Exchange. This is the first pick protocol. Yeah, in this one actually it basically is a DFA-HAMR exchange, but the DFA-HAMR exchange is not secure due to the man-in-the-middle attack. So here in this protocol, we use password. Just use password as a symmetric key, and to encrypt the temporary public key for the DH protocol. Yeah, in this way, you can get a secure protocol secure protocol. About the security, actually, it can be proved secure under the random outcome model. Yeah, but we need to assume that the symmetric key we used for encryption here is an ideal cipher. So it has no flaws, like an ideal cipher. Yeah, just an ideal cipher. A second one called the SPEKE, simple password exponential key exchange. We just based on this one, get our new protocols. And this protocol is doing it in another way, still based on DH. But here we just use the, I don't know which point is this one? Maybe not working. Sorry, which one?
No.
No, okay. Just forget it. So in this protocol, basic idea is that actually we generate the generator for our multiplication group G from the password user hash function. Actually, this is also related to the previous presentation about the hashing some value to a point in ECC. Yeah, it's related. So the proposal from my point is also interesting. So thanks for that. Just for this one, so this basically means the attacker can still get the temporary public key for the DH, but they don't know what is the generator because they don't know the password. Yeah. So from this point, it's quite simple. But the proof is not so simple. Yeah, especially saying that the available security proof only works for a multiplicative subgroup of finite fields, not for the ECC groups.
Really?
So this means if you use ECC, you can still use this protocol, but it's risky because no security proof guarantee for this protocol. Yeah, and also because of this reason, so actually the real efficiency for this protocol is not so good. Okay, so here we introduce our protocol. Our protocol in some sense is quite similar to the PEKE. Due to this reason, we call it two-base PEKE. So in our protocol, we just get the generator G from two bases, U multiplied by to PW. PW is the password. U and V are the two bases. This is our protocol. Yeah. And the next one, to prevent the server corruption, so we need to do it in another way, just based on the first protocol. So what we do is that the client side still need to hold the password. But for the server side, the server only need to store another value. It is called the V to the H SPW. S here is just a random sort. Yeah, for each user it is different. And the H here is a hash value. Yeah, so this means it's the server side. The server doesn't need to store the password. Yeah. And in the implementation or in how to design the protocol, the basic ideas. The first idea is that, the user need to prove his knowledge. HSPW is the hash value of the password together with a random sort. Yeah, he needed to prove this one. And to prove this one, basically, they will use the zero knowledge skill. So also just the previous slides introduced the idea. Here we don't mention the detail. And the next part is that because zero knowledge proof is like a 3-move proof. There's a challenge, commitment, challenge, and a response. And in this one, we must need to encrypt the response. Otherwise, the protocol is not secure against the offline dignitary attack. Yeah. So detail is a little bit complex, but the basic idea is just this one.
Can I just interrupt you? So there are 4 minutes left. You can either keep going through your slides and have no time for questions, or
okay, just maybe just 1 minute is okay.
Yeah.
Yeah. So here is about the security proof. We actually give a security proof in different cases. Yeah, like whether it is supported security, and we also consider the password so that we can get a little bit more tighter security results. Yeah, there's some examples, so we don't need to go into detail. Here is the comparison. So in the second part, the last line is about our just the PAKE protocol, how it is efficient. From here, you can see it supports both forward security and also works in the ECC group. And the last part, in the last line, show our verified version of our protocol. It also supports the forward security and also works for the ECC. Here is our preliminary implementation. This is the recommendation of parameters. So in different security levels, what's the password we can use? How long the password and the corresponding ECC element size. And this is our preliminary implementation result. Basically, in our a quite normal server, so each protocol can be run. I mean, mainly for the computation, can be done in 10 milliseconds. This is the requirements from RSA 8125. It is about the requirements for PAKE protocols. So 8 requirements here. So we can say our protocol satisfy almost all the requirements. Yeah, some we need a little bit more work. So we think it could be a candidate proposal for these requirements. So that's all. Thank you.
All right. Quickly, questions, please. And
Philhan Baker, I would just like IETF to pick exactly one. I don't care what it is, so long as you pick one and it is patent unencumbered, which is the reason that we're not doing any of this today, because there were patents and they got in the way.
Dan Harkins again. So related to what Phil said, requirement 8 is you have to say whether your company has any IPR in this scheme. So does your company have any IPR in this scheme?
We don't have.
Okay. So on the comparison, you say that SPAKE2, SPEAK, and SAE do not provide forward secrecy, but that's not true. If the password's compromised, if SPAKE2, SPEAK, and SAE, they all provide forward secrecy.
SPAKE2, right?
Yes. They all provide forward secrecy. And I don't think that there's a limitation for a multiplicative subgroup of finite field for SAE.
Okay, we check it later maybe.
Okay.
Yeah, discuss with you. Yeah,
Stanislas Michlev, CryptoPro. I would like to add a few words to the Dan's comment. In fact, SPAKE2 has forward secrecy. Moreover, Dan's protocol PKX has it, and as I understand, has all positive features that you enumerated in your slides. So it will be very good if you, maybe in the mailing list, we could have a deeper analysis of comparison of your protocol to all existing ones, because you have a lot of packages, and I think that at least 3 of them are quite similar in the sense of its security. With forward secrecy, with support of elliptic curves, and maybe the difference is about the complexity, the additional security properties, and also I would add that your definition of verifiable PAKE seem very similar to augmented PAKE, and in fact, this doesn't prevent as a password to be leaked if the server is compromised. It's just another line of defense if the adversary wants to brute force all passwords. But if he wants to attack one single password and he knows this verification value, it's not a big problem. So, and I would like to add to continue this discussion in the mailing list because it can be very long.
Okay.
Yes,
Thank you for your
I
comment.
think, yes, sorry, we're a bit short on time. So yes, let's take it to the mailing list and we'll follow up privately. All right. Thank you.
Okay.
Thank you.
Benoit? Hmm? Yeah. You can.
Hello, everyone. I'm Benoit Viguier. I'm from Radboud University, the Netherlands. I will be presenting the draft for Kangaroo 12. So first of all, what's Kangaroo 12? So let's have a look at Check 128. Check 128 use a sponge construction. So basically, you have your sponge on your right, which is divided into two parts, the outer part and the inner part. The inner part is what guarantees the security of the scheme. And in this sponge construction, you are going to split your message into small blocks that you will absorb. And between each absorption, you will apply a round function, which is mixing up the inner part and the outer parts. And then once you've mixed up everything, you want to extract your hash, basically. So basically, you extract a small part, and then you mix again and extract. The point of this is you can extract as many bits as you want, so that's why we call it an extendable output function, because the length is arbitrary, as long as you take long enough. In the case of Check 128, you use a Ke function, which permutation that has been defined into FIPS 202. So while Check 128 is quite nice by design, it does not allow the possibility of parallelism, which makes it a bit slow. So we want to put some steroids into that using Kangaroo 12. So basically, Kangaroo 12 is the same idea, but we apply a tree structure with the sponge. So you split your message into block of 8,192 bytes, so that you see in blue there, and you will hash these small blocks into what we call a chaining values that you see in green there. That will be 256 bytes. And then you will hash the full thing again. So we use the same sponge construction, so we're also pretty nice in terms of design, and we reduce the number of rounds of Ke to 24 to 12, giving us already a bit more speed. And as you can see that the longer the message, the more parallelism you gain. So, and it also, if you have short message, you don't need to actually hash the other part, so you actually don't have penalties for short message. So once you see that, you start thinking, what's the security of it? So Kangaroo 12 is claimed as secure as Check 128. In other words, 128 bits of security. It has, because it uses a sponge construction, you also relies on the generic security of a sponge that has been provided by the Ke team. The parallel mode is based on Sakura tree hashing, so it's also proven secure by the Ke team once again. And on top of it, we have the same round function as defined in FIPS 202, so Ke, but only with the 12 last rounds. This means that the cryptanalysis that has been applied to it is still valid since like the last 10 years. And we moved on from a safety margin, which is rock solid, to quite comfortable still. As a matter of fact, if we have a look at the 24 rounds of SHA-3 here, we still are in the middle of it. We have collision over 5 rounds, but we also have collision over 6 rounds, but with a smaller capacity. So this gives more degrees of freedom. The difficulty of having a collision of over a capacity of 160-bit is estimated, if you take a birthday paradox, as to the power 80. We also have stream prediction over 8 rounds, but we have 12, so it's fine, with a difficulty of 2 to power 128 time. It's also possible over 9 rounds, but the difficulty is 2 to the power 256 time, so that's already above the security claims. That's really fine. And there have been lots of third-party cryptanalysis being done on Ke, so that's really nice. We've seen that
Control 12 is pretty secure. Let's see how fast it is. We have the number of rounds, so it will logically take half the time. So it's twice faster as check 128. And then once you take longer inputs and the latest Skylake X processors only using AVX instruction, then you can get down to 0.55 cycles per byte. At that point, the bottleneck is not the hashing anymore, but more the network connection and so on. So why I think it's an interesting RFC that we could have, it's because it's on the same basis as the NIST. It's public design, completely open. It has been the result of the SHA-3 international competition. It survived 10 years of cryptography and cryptanalysis, and still will, I hope, survive more. It provides a really nice speed up with respect to SHA-3 without wasting any cryptanalysis resource, because what have been done in the past still applies today to Keccak and Kangaroo 12. And the parallelism just scales with the implementation. So you don't have to provide additional parameters like I want to have Kangaroo 12 with 8 parallelism computing at the same time and so on. So that's really nice. For more details, I can invite you to have a look at the current draft. Also, I will add that there is a version 2 that will be published online very shortly. Thank you for your attention.
Thank you. Questions, comments for Benoit? So I'll start off maybe until people can get to the mic. So you've half the number of rounds in...
Yes.
So what percentage of your performance gain comes from halving the number of rounds?
We are at least twice faster than check 2, so, and then we have the cycles per byte counts.
Okay. So it seems like something like 70 or 80% of your performance gain comes from just halving the number of rounds.
No, it also comes from the fact that we are actually hashing in parallel the blocks and not using the fact that we have to process every blocks one by one, just as in check 3 or check 128.
Okay. It's a question from the floor.
Oh, yes. So here is Guiling. So I would like to know, Kangaroo 12 is basically like a primitive to construct the block cipher or hash function, or just a complete algorithm?
It's a complete hash function, a complete extendable output function. So you provide the message. You can provide an optional label, but that's, if it's not provided, then it's considered as empty, and you provide the output length that you want.
Okay. Yeah. Thank you.
Nick Johnson, Ethereum Foundation. It seems like you're combining two different trade-offs here. One is, two innovations, I guess. One that improves speed with parallelism with no cost and security.
Yeah.
And a second trade-off which gives you more speed at the cost of additional security. Why combine these together? Why not just offer a parallel construction that uses the existing number of rounds?
Well, if we want to have a very nice speed up, it's even better if we can actually decrease the number of rounds. Like the current Keccak implementation with 24 rounds is like really, really conservative, and there is no lots of going down to 12 rounds.
Is there a reason that you believe that your users will be will need less conservatism than general Keccak consumers?
The security claim is the same, so there is not really less conservatism in that case. Like we still have 128 bits of security.
That's under an assumption that reducing the number of rounds doesn't weaken security.
Yeah.
Okay, so it's not it's not an unconditional assumption, right?
Well, until proven contradict.
Are you able to go back to the slide with the performance measurements for a moment?
That one?
Yeah, so it looks like you're getting, comparing the short input to the long input, you're getting at least 100% speed up from parallelism as well.
Yes.
I guess I still don't understand the justification for the two changes together. It seems to me like it'd be a very useful construction with standard Keccak. But
well, standard Keccak would
you would have the same speed at check 128 for inputs that would be shorter than 8,000 bytes, basically.
Yes.
And we actually want to try to make everything faster for whatever the possibilities. So that's kind of a trade-off.
Thank you.
Okay, we're kind of over time, actually. We're already eating into people's break. So I think we'll need to leave it there, and we can maybe take further discussion of the draft to the list, if that's okay. Thank you from the chairs for attending this session. Stay here if you want to attend the next session, which is TLS Working Group, starting in about 15 minutes. And could we please have the blue sheets back to the front, please? Would somebody bring them down? Thank you. Thank you, everyone. Thank you.
Thank you. Luckily, I have a conflict, so I need to be elsewhere.
Okay, I'm going to stay here.
Yeah, I know. So are you here? Yeah, it was good. Are you here all week or?
No, I can only be here on today and Wednesday.
Okay.
There's a lot of other stuff going on at Royal Hallway that I need to be involved in because we've been on strike for weeks.
Yes, Akra was asking me, do you know what this strike thing is? And I said, well, I'm not sure. You better.
Yeah. Thank you.
So
it's about pensions they want.
No.